Welcome back, everybody. Today, we talk about reinforcement learning, RL. We also hear people refer to this as sequential decision-making under uncertainty. In the core course, we already saw the RL machinery, the MDP5 tuple, Q-learning, value iteration, or greedy policies. Today, we look at the same setup from the modeling angle. In particular, every real RL system out there starts as a messy problem that someone decided to write down as an MDP. In other words, we translate a real-world problem and application into some mathematical form. And someone has to do that translation, and the choices they make matter. So the question for today is, well, how is that translation, that conversion actually made? What do those choices imply? And which part of the translation is perhaps the hardest, and why? We'll work toward the answer over the course of today. Let's start with a quick reminder of the canonical picture. Mario in a grid world. So there's no manual, no walkthrough. No one tells Mario which squares are safe. Each step Mario takes just gives him a new position and a reward, perhaps +1 for a coin or a -10 for a pin. The only feedback for Mario is what happened, not what he should have done, just the result, just what happened. This is learning by doing, as we know. And we already know also how to solve this game if we're handed the grid, the transitions, the rewards. But this picture is hiding the modeling questions, namely who decided the state space, the action set, the reward signal. For this Mario game in a textbook example, the answers seem almost trivial, but real problems out there are rarely this clean. Zooming out a bit, another helpful reminder here. Well, how does RL compare with the other learning paradigms we've seen? So here we show a table. There are 3 columns: supervised, unsupervised, and reinforcement. On the data row, supervised gets a labeled dataset. Unsupervised gets unlabeled data, and RL has no fixed dataset. It collects its own data through its own actions. On the feedback, supervised gets the correct label, unsupervised gets nothing and finds structure, whereas RL gets a reward signal, just good or bad. On the go, supervised predicts the label Y from the features X, unsupervised model the distribution of X or generates samples, and RL roughly maximizes the total reward. If we use analogies, supervised is like studying from a textbook with answers written. Unsupervised is staring at raw data and look for patterns, whereas RL is learning to ride a bike. The point worth keeping in mind is, in RL, our actions change what data we see next. If Mario goes left, he never sees what was to the right. The data and the policy, they are coupled. A bad choice of state or reward can lock us into a region of the world we never escape. Now, with those reminders in hand, here's the plan for today. First, a quick refresh of the RL loop, the notion of policy and trajectories, slightly more formally, just enough to review the notation. Then, we are going to break the lecture into 3 big parts. First part, why is RL challenging? We're going to look at it through 4 particular failure modes. Part 2 is using MDP as a modeling language. We're going to apply that to 5 real systems. For each of those 5 systems, we're going to map the problem, the application, into the MDP formulation. And we're going to ask who got to choose each and every one of those 5 tuples. And then part 3 is about the reward. Perhaps this one is going to be a little bit surprising because, well, as we will see, there are quite some nuances around the rewards. Throughout, the common thread is the choices that we make to turn an application, a real problem, into an MDP. And throughout, what does each of those choices cost us? Let's go over the high-level RL review now. Here's the familiar picture. Agent on the left, environment on the right, action goes out, state and reward come back, and we repeat. 2 things worth noticing. First, the boundary between the agent and the environment is itself a modeling decision. Take, for example, a robot with arms and joints reaching for a mug on the table. In one setup, the whole robot body is the agent, joints and everything. The environment is the mug, the table, and the room. In another setup, the agent perhaps is a computer program, maybe even an AI agent someone vibe-coded. And that AI agent is living on some chip inside the robot. And this agent is sending high-level commands to a separate controller inside the robot, whereas the joints in the robot body is just responding to those control commands. So in that setup, the AI agent actually corresponds to the agent in this picture, whereas the robot, the joints and stuff, they become part of the world, part of the environment. It's the same robot, but we just looked through two different setups, and they lead to two different RL problems. And we are the ones drawing the line, which changes what the policy actually has to learn. So our modeling decisions have downstream effects. Second, the reward signal lives on this boundary. Whatever crosses that arrow is what the agent will optimize. So the reward is the only handle we or the agent have on its behavior. Quick refresh on policy and trajectories. A policy pi maps state to action. A policy could be either deterministic or stochastic. The diagram here shows both policies for the same situation. Mario has a coin to his right and a pet straight ahead. On the left of the diagram, we show a deterministic policy written as pi of s equals a, meaning that when we're in state s, we're just going to choose the action A with full certainty, so 100% probability assigned to this particular action A. The deterministic policy put all of the weights on the action right in this example. On the right of the diagram, we show stochastic policy written as pi of a given s. So this is a conditional distribution. It tells us when we are in state S, what is the distribution over all the possible actions A, and the stochastic policy just spreads the 100% probability quota across multiple actions, leaving some room for possible exploration, not fully committed to a single action. And that covers policy. Our goal in MDP is to find pi star, an optimal policy, a policy that maximizes the expected sum of discounted rewards across trajectories. And here's the trajectory unrolled in time. We start in some initial state S0, the policy picks up an action A0, the environment hands back a reward R0, then comes in the transition. And here notice that there are two arrows into the next state. One comes from the previous state, one comes from the action, and both would shape where we land. Now that we're in S1 and then the loop repeats, we get A1, R1, and it keeps on going step after step, all the way to the horizon. The final steps at H-2 and H-1. We call this whole sequence a trajectory tau, and the full tau is what an RL algorithm gets to look at, gets to observe in order to update the policy pi. So that is the whole setup. We observe, we act, we get a reward, we repeat. It looks very simple, but in practice, RL is much harder, much harder than supervised learning, and there are many reasons for it. Here in part 1, we will focus on 4 particular failure modes. So the first big challenge is the so-called credit assignment problem. Imagine we win a chess game after 50 moves. Well, which moves get the credit? Is it the opening, the mid-game sacrifice, the final checkmate? Well, we don't know immediately. Compare that with supervised learning. Well, every example has its own label. We make a prediction, we get immediate feedback. The credit is instant. Whereas in RL, one reward can come from a whole sequence of actions, and we have to untangle which actions and which decisions actually mattered, which were irrelevant. It gets worse when rewards are sparse. In the game of chess, well, the only meaningful signal comes at the very end. Did we win or did we lose? So we would have to try to figure out which of the 50 moves were responsible for the very end result. We actually also face this type of issues in everyday life too. Here's a cooking analogy. Say our cake tastes terrible. Was it the flour ratio, the oven temperature? Did we take out the cake too early? Well, every step was a decision we made, but the only feedback came at the very end when we tasted the cake. And that's what RL agents have to deal with constantly, this delayed feedback. Second challenge is self-generated data. In supervised learning, the training data is fixed. It doesn't change with the model. In RL, the agent creates its own data, and that sets up a dangerous feedback loop. Suppose we start with the bad policy. Because the policy is bad, it only visits a limited part of the world. So we get limited data. From that limited data, the agent learns a biased model. The biased model produces even worse policy, and we go around again. Compare this to supervised learning, where a bad model that we come up with is just bad in isolation, be it a linear model or a neural network. Well, whatever model we throw at the data, it doesn't really change the data itself. We can just try the same data, maybe use some other hyperparameters or another hypothesis class or another modeling assumptions, well, to come up with a better model. In RL, a bad policy literally changes what data we collect next. We might never see the good parts of the world if we started out with a bad policy. This should also remind us of our domain shift discussion. And here, the data distribution depends on the very thing we're trying to learn. And the dataset and the learner, they co-evolve. And a bad start can compound very quickly. The third challenge, and it's a cousin of the self-generated data. If the agent's own actions decide what data we get, then every step we face a tension. The cleanest way to feel the tension is through this problem that Feynman framed as the restaurant hunting problem. So imagine picking a restaurant for dinner. Do we go to our favorite, exploiting what we already know that we like, or should we try the new place that just opened? It might be amazing, it might be terrible. We won't know unless we try. Picking the favorite is obviously the exploit. It's greedy, it's safe, but we might get stuck at a local optimum. Trying a new place is naturally the exploring. It costs us tonight. We might have a bad meal, but it could lead to a new favorite place, even if the first visit is underwhelming. So in general, too much exploitation and we might never discover better strategies, whereas too much exploration and we might waste time on actions we already know are bad. And getting this balance right is one of the fundamental challenges in RL. One subtle point beneath the surface is that exploration isn't always cheap. Sometimes it's not even possible. And A/B testing, for example, is the everyday version of this. Say companies want to choose between two product versions, say two ad layouts or two ranking algorithms or two pricing strategies. Say Amazon wants to do this. Amazon split users into two groups. They show each group a different version and then measure which one performs better in order to make some informed decision. The cost of that exploration is bounded but real. Some users get the worst deal, some get the worst variant, while we figure out which one of those two versions, A/B versions, wins. Medical trials work almost the same way, but the stakes are much higher. Say we want to assign real patients to a treatment group versus a control group. Well, maybe the treatment can turn out to be worse than the control, or vice versa. And sometimes that might even come with permanent harm. And so we have to think in terms of the real patient outcomes. Self-driving cars push this even further. So random exploration on the road means real injuries or even death. So the cost of exploring ranges from, say, a worse user experience to genuine danger. And in some cases, we can't just do it at all, which means that, well, the exploration versus exploitation, it's not just the theoretical challenge. In practice, there's also nuances associated with it. Fourth challenge, RL agents are incredibly data hungry. AlphaGo, the famous deep RL application, it needed about 30 million self-play games to master the game of Go. OpenAI 5, which learned to play the game of Dota 2, needed about 10,000 years of in-game experience, compressed into days with massive parallel simulation. So why does RL need so much data? Well, first, if we compare that with supervised learning, say computer vision, CV, or NLP, CV and NLP, natural language processing, they could scrape the internet for billions of images, trillions of words. The data is just out there. Whereas for RL agents, they have to interact with the world for each single data point. And each individual interaction only gives a very tiny signal, one scalar reward. Similar comparison can be made for RL with a human child, compare that with a human child. A child can learn to walk in about a year, not through millions of trials. They just get more efficient feedback, dense feedback from every wobble. Well, is it the balance, proprioception, vision, maybe a parent is nearby steadying them? So there are strong priors baked in, built in, and RL agents have none of that. Now here's the real callback kicker. Even if the game of Go or Dota 2, they are data hungry, we can at least simulate them for free. Almost. It's just software. It's pretty cheap to simulate. But we can even cheaply simulate things like surgery, medical trial, driving, or customer interactions. So in those domains, every data point comes with real experimental cost. It's money or time or risk. So those are even beyond the exploration versus exploitation trade-off. So those are the 4 parts about why RL is difficult. Now we dive into part 2, modeling practice. And let's pick up the MDP from where the core course left it. In the core course, MDP was the given. Someone hands us this SATR gamma, this 5-tuple we're going to review. And our job was just to solve for a pi star, an optimal policy. Whereas today, MDP becomes the question. Given a real-world problem and application, what should the 5-tuple be? And let's review the 5-tuple. So we're going to look at the symbol, the name, and the meaning. So here, S, capital S, is the stage space. It's just everything the agent gets to observe about the environment, about the world. A is the action space. It's everything that the agent can do. T of SA S prime is the transition. It's the probability of landing in state S prime when we take an action A from state S. R of SA is the reward. It's the immediate payoff for action A in state S. And gamma, between 0 and 1, is the discount factor. It's the knob that trades off rewards now versus rewards later, like delayed gratification. Markov means memoryless, meaning that once we know the current state, the past history should not add any information about what's going to happen next. And that assumption is what keeps the math tractable. If we know all the 5-tuple, all these 5 rows, including the transition and reward, then it's a known MDP. And we can solve it by using planning algorithms like value iteration or policy iteration and so on. In RL, we do not know the transition T, and often we also do not know the rewards R either, so those rows are crossed out. So instead of crunching numbers in some almost closed form formula, the agent has to rely on interaction, has to try actions, observe, then improve through algorithms, stochastic algorithms like Q-learning. So it might also be worthwhile to call out the framing. From an algorithm point of view, MDP and RL, they deal with the same framing. They all deal with the 5-tuple. The only thing that changes is the amount of information an algorithm can walk in with. In MDP, everything is known, so we really just have to crunch some numbers, calculate something. In RL, some quantities are unknown, like, for example, the transition probability. You can think of it as, say a coin. A coin always has some real intrinsic probability of landing heads if we flip it. But if we pick up a random coin off the street, we don't naturally know what that probability is. So that probability exists, we just don't have access to it. We just don't know what that number exactly is. And that is the distinction of what an MDP algorithm versus an RL algorithm has to deal with. The RL algorithm knows that there's some transition probability, just doesn't have access to that particular number. And for the rest of today, we walk through 5 problems in a slightly deliberate order. So the first one actually feels like textbook RL, and the last one will barely look like an RL until you kind of force it through the MDP language. So example 1, this is the closest to Mario. It's a robot learning to walk. Well, the stage space here naturally covers everything the robot can sense about itself, right? Joint angles, velocities, balance readings. The action space is the torque applied in each motor, which is continuous rather than discrete. The transition is where the first real modeling difficulty shows up. We know that there's physics underneath. There's a friction, there's gravity, momentum, but we can't write down the equations very precisely. So we have to treat the transition as unknown. Again, think of the coin example. We have to treat the transition as unknown and let the robot learn the transition by trying out things. The reward is something we design, and we can keep it simple here. We can say maybe +1 for moving forward, -10 for falling. And that simple version is useful for illustration. In a real robot, though, the reward often has many terms, as perhaps a forward speed, staying alive, so on and so forth. And we actually will come back to that later, because every extra term adds coverage, but also makes the reward more fragile. And here, gamma, back to the robot learning to walk, simple example. Here, gamma is high, but strictly less than 1, because the robot needs to plan ahead, since avoiding a fall right now matters, but it also matters to make progress over many steps. And we keep gamma below 1 because walking has no natural end. The agent could just keep on going forever. So the discount is what keeps the value function finite. The video on the right is Russ Tedrick's toddler robot from 2004. The remarkable part here is that Russ didn't program the walking gait. The robot just discovered the gait entirely by trial and error, just by optimizing this reward function. I guess another impressive thing as a pure aside was that Russ actually built the hardware himself in-house. Anyway, back to the RL formulation. So for the robot, both T and R, the transition and the reward, they take some real work, but T is the transition is the more prominent pain. Because complicated physics is hard to model precisely, and even our simple reward is already somewhat of a proxy, because it's only a standing-in replacement for what we actually want. What we actually want is stable, used for locomotion, and we reduce that to a single scalar function. Now example 2, AlphaGo, the famous milestone system that I mentioned. So it's the system that actually beat the world champion at the game of Go. It's the same, we can model that by using the same MDP framework, but the transition here shows up differently than it did for the robot. Let's walk through the modeling for this case. Well, the stage space is obviously the board configuration. It's a 19 by 19 grid where each grid cell can take on black, white, or empty. So there can be up to 3 to the power of 360-ish board configurations, or roughly 10 to the power of 172. It's vastly more than the number of atoms in the observable universe. The action space is where to place the next stone, so there's about 360 moves at the start of the game. For the game of Go, the board update is governed by the rules of the game, which are crisp and written down. Placing a stone leads to a board state we can compute exactly. But transition T isn't just about our move. It also includes the opponent's replay, and the opponent's replay is not part of the rules. If we play against a human opponent, that replay is unknown, and we have to model it. And AlphaGo bypassed this challenge by training largely through self-play, whereas the opponent is just the agent's own current policy. So the agent, the robot, is playing against itself. In that setup, transition now becomes known, because we know the policy on the other side as well. But that known is still not the same as deterministic, so there's still some randomness coming from the stochastic policy. Now, the most natural reward is as sparse as it gets, +1 for winning, -1 for losing, maybe nothing in between. We can play hundreds of moves and only find out at the very end whether any of the moves were any good. For the discount factor, gamma naturally is 1, no discounting at all. A game of Go has a definite end, and once the trajectory terminates, there is nothing further to discount. So this is the general pattern. Gamma equals to 1 is fine whenever the horizon is bounded. Contrast that with the walking robot where there was no natural end and gamma had to stay below 1 in order for the infinite sum of rewards racked up across a trajectory to stay finite. As a side note, some Go variants have a speed clock, and there a gamma strictly below 1 would actually be very desirable because it would push the policy towards winning quickly. So on the right here, we have this game 2 against Lee Sedol, a human Go champion. In this picture, AlphaGo played this move 37. And that move stunned every human expert watching the game, because it looked so bizarre at the time, but it turned out to be a brilliant move. That is RL finding moves beyond human intuition. In fact, nowadays, a lot of the human Go players, expert Go players, they would actually watch AI playing the game in order to find inspiration. So back to the AlphaGo game here, well, the transition T isn't really clean. It's just hard in a different way than the robot case. And the reward isn't trivial either. We have to play hundreds of moves and get no signal until the very end, so the trajectory is long and uninformative. You might wonder, if that is so difficult, why don't we just assign a goodness score to transient board positions and use that as intermediate rewards? Well, that is actually the credit assignment problem in another disguise. And it's also have this the chicken and egg situation or flavor to it. Well, because if we already had a precise way to evaluate any board position, then we wouldn't have to do RL at all. We could just do supervised learning. Well, you hand me a board, I evaluate the board, use whatever goodness score you propose, and then I'll just play the move with the highest predicted score. So right there, we already see that, well, natural and intuitive rewards, they could either be hard to implement or uninformative. Example 3 is chip placement. First, what is chip placement? And think about Apple designing the motherboard for a new iPhone. On a fixed piece of silicon, engineers have to decide, well, where to put every functional block, the CPU, the memory, the cache, or the radio. At first glance, this looks like a static layout problem. It's not an RL one. The reason that this can be formulated as RL is that, well, chip design happens one block at a time, and each placement constrains what comes next. And that sequential nature is what makes it a sequential decision problem. There are several challenges associated with this problem. One of them is just the size of the problem and the nature of the decision variables. Because this is an optimization problem with two kinds of variables. There's discrete variable, because we have to decide which component to place and in what order. There's also continuous variables, well, because we have to decide where exactly on the canvas each component would land if we chose to choose to place it. And that combination explodes fast. A real chip has thousands of components and essentially infinite space of positions for each one of them to place. Google, through the work of AlphaChip, formulated this as an RL problem. And in their formulation, the state is the partial layout so far, along with connectivity and congestion information from what has already been placed. The action is to drop the next component. It's a functional block somewhere on the canvas. The transition is essentially deterministic once a component is placed. The routing constraints update for everything that follows. The reward penalizes wire length, congestion, and area. And we want components close to each other when they need to communicate, but not so close to the point that they might create bottlenecks. Gamma is 1 again. It's the same logic as AlphaGo, because the process terminates once every component is placed, so there's nothing further to discount. The figure here is from Google Research, the AlphaChip work. The agent places components one at a time. Then a separate method fills in the smaller standard cells. And in that work, the reward combines wire length with congestion. The structural challenge is that one early placement can create congestion problems that don't show up until many, many steps later. So that long horizon sequential dependency is what makes it a natural fit for RL, but also where the difficulty comes from. Now here, the transition T is mostly clean again. The difficulty moves to R. The reward has to compress many engineering goals into one score. And different design of the reward just mean we're going to have a different chip coming out of the other end. Example 4 continues to be not so obvious, TikTok's recommendation algorithm. So it turns out TikTok modeled this as a MDP by saying that the state can capture whatever the platform knows about the user in the moment, their user profile, their watch history, the time of the day, and the device they're on. The action is which video to show next, drawn from a candidate pool of thousands of videos. The transition is unknown and in a deeper way than the robot example, because how does a user's internal state actually change after watching a video? Do they get bored, energized, angry, or happy? We can't observe that internal state directly. We can only see what the user do next. The reward continues with this nuanced difficulty, because we have to decide, well, should we reward watch time, the number of likes, the number of shares, or maybe some weighted combination between the ideas? And the choice itself is a design choice. It matters enormously downstream. And gamma controls the time horizon. A high gamma pushes the system towards long-term retention, like keep the user coming back tomorrow. A low gamma pushes it towards engagement right now in this session, because maybe down the lane, the reward is going to count much less due to the heavy discount. Now, coming back to the reward discussion, is watch time actually a good reward at all? We might watch a 10-minute drama unfold and perhaps feel worse afterward. The algorithm counts that as 10 minutes of engagement, so perhaps a big win on the metric. But was it really a big win for us, the users? There's that gap between metric and goal, and it actually has a name. It's called the proxy reward problem. With TikTok, both the transition and the rewards are uncomfortable. The transition T, they hide inside the user, whereas the reward R is actually a social proxy. We'll come back to the proxy problem in the reward part. The last example pushes the framework furthest. RL isn't limited to games and robots or social platforms. DeepMind actually used it to solve a pure mathematics problem. And here's the setup. We all know how fundamental matrix multiplication is. Well, it appears everywhere in all sorts of engineering problems that we are trying to solve. And if we can do matrix multiplication fast, well, then the implication is enormous, because as a stepping stone, as a key subroutine in a lot of things that we do, if we can do that subroutine very fast, that would just improve the overall efficiency of the full stack algorithm that we're trying to apply. And in particular, there's this well-known case that, well, if we were to multiply two 2x2 matrices using the textbook way of multiplying a row with a column, do pairwise multiplication, sum up the products into the scalar entry for the output. So in the 70s, in 1969, there's this mathematician named Streisand. He found a clever trick that by rearranging terms, he only needed 7 operations to perform this 2x2 matrix multiplication. It was a landmark result. So the natural follow-up question is, can we do better for larger matrices? As it turns out, for most sizes, for most matrix sizes, the minimum number of multiplication is still an open question. And mathematicians have chipped away at it for decades, finding small improvements case by case, but there's no general method. And in the 50 years after Streisand, nobody even improved the 2x2 bound. In fact, people have proved now that 7 is in fact the best upper bound, achievable best upper bound. You cannot do better than 7. For a lot of the larger size matrix multiplication problems out there, the question remains open. So DeepMind asked, can an RL agent help us search this space faster than humans can possibly do by hand? Can we discover something in that field? So DeepMind reframed the search for matrix multiplication algorithm as a single-player game. And here's the idea. It's actually pretty clever, so let's go over this slowly. A matrix multiplication can be encoded as a 3D tensor. And rank 1 term of that tensor is essentially one scalar multiplication's worth of the structure. If we can decompose the 3D tensor as a sum of k rank 1 terms, that gives us an algorithm with k scalar multiplications. The standard 2x2 algorithm decomposes into 8 rank 1 terms, and Streisand's way, well, he just found a decomposition into 7. For larger matrix sizes, the minimum number of rank 1 terms is what we'd like to push down. So finding a shorter algorithm becomes the same problem as finding a shorter decomposition. That is the least natural MDP so far. And slot by slot, the definition in the MDP5 tuple, the state is the residual tensor that still needs to be decomposed. So the agent starts with the full tensor, that is the full product, and subtracts off one rank 1 term at a time. It's trying to drive the residual to 0. The action is the next rank 1 term to subtract. It's to pick which entries to combine to form the rank 1 term. The transition is deterministic. Subtracting the chosen rank 1 term updates the residual exactly, so you arrive at the next state. The reward pushes the search toward fewer multiplications, so a natural choice would be a -1 per step, plus a large bonus when the residual hits 0. So naturally, you would have this incentive to take fewer steps and drive the residual to close to 0. Gamma, the discount factor is 1. The process terminates once the residual is fully decomposed, so there's nothing further, nothing future to discount. So with this formulation and a lot of search in solving this RL formulation, Alpha Tensor actually found new bounds that is better than the best known results thus far for several special cases. And the more remarkable thing is, within days of publication, human mathematicians actually built on the AI discovery. And the humans, they found even more improvements. And that is yet again RL helping humans discover new things, new ideas, in this case, new mathematics. And if we take a step back and revisit the modeling process, well, the difficulty moves actually to the abstraction itself. Someone had to invent cleverly the state representation and the action representation before RL could even start. And even there, someone had to decide that multiplication count was the target and that extra additions were an acceptable trait. Let's step back from the 5 examples. The MDP gave us one language for very different systems. We looked at robots, games, chips, recommendation systems, and mathematics. But a different role, and sometimes multiple different roles, they can hurt each of these systems, each of these modeling practices. For robotics, we saw that T, the physics, the transition, it can be hard to model. For the game of Go, the reward was clean but very delayed. For chip placement, the reward R has to compress competing design goals. For TikTok, internal human states were hidden, it was very difficult to model, and the reward R was actually a social choice. And finally, for Alpha Tensor, the state space and action space, they had to be cleverly invented. And that is the pattern. Writing down this 5-tuple SATRN gamma is not just bookkeeping, it's not clerical work, it's the entire modeling act. Now we actually zoom in into the role that most often carries the human intent, the reward R. What we reward is what we get, for better or worse. It's actually very easy to get the reward wrong, and to get it right, there's oftentimes many nuances associated with it. So here's the golden rule, and it's worth internalizing. The agent will maximize exactly what we tell it to maximize. Nothing more, nothing less. It sounds obvious. It's almost a tautology, but it's the source of most RL failures in practice. So why is it causing failure when agent tries to do the work? The problem is often that RL agents are too clever. They find loopholes in our reward function that we never anticipated. Since RL agents are optimization machines and they have one single objective in mind, maximize the rewards, they will exploit every gap between what we specified and what we actually wanted. Here's a classical example. an RL agent playing a boat racing game called Coast Runners. The intended goal, what the designers wanted, was for the boat to finish the race as quickly as possible. The specified reward, what the designers actually coded up, was points for hitting checkpoints along the track. So what happened? The agent just found a small loop of 3 checkpoints near the start. So instead of racing toward the goal, the agent just drove in tight circles, hitting those same checkpoints over and over. It caught on fire, it crashed into other boats, it doesn't matter. The agent was just racking up infinite points without ever finishing the race. It's shown here in the animation. So the agent did exactly what it was told. The problem was what it was told. There was a gap between finishing the race and hitting the checkpoints, and the agent just drove the boat right through that gap. Another tricky thing about rewards is that they get messy pretty fast. We looked at this example of a simplified case of a reward for keeping a robot up, and we understand from the discussion on the game of Go, the sparsity of the reward can be challenging to deal with. Nowadays, a typical reward, for example in locomotion, for a walking robot, is often a weighted sum. There's forward velocity, a live bonus, those would be positive terms inside the sum, the torque, high deviation, action smoothness, some other quantities, and they may be the penalties inside the sum. And each of those linear combination coefficients is a hyperparameter that engineers have to tune by hand. Engineers have to spend weeks tuning these hyperparameters, and every single one of them opens up a new failure mode. If we penalize torque too much, the robot might freeze. It's too afraid to move now. If we penalize it too little, we might get violent, jerky motions. Adding a new term to the whole sum, to the whole mix, it might fix one behavior, but we might very likely break another behavior somewhere else. So at some point, the reward function becomes its own engineering project, and oftentimes it's harder than building the robot itself. That is why people often now study reward design as its own problem. As an aside, these rewards functions look nothing like how humans actually walk. None of us track our joints' velocities or torque budgets when we take a step. So as proud as I am of being part of the robotics community about the advancements that we're making, it's still an open question as to how we can close the gap between, say, artificial intelligence and real human intelligence. How could we make our robot, make our optimization a little bit more closely resembling the human walking gait? So back to our main discussion, what do practitioners do about reward design? So there's no magic recipe, but 4 principles might come in handy. They might help. First, it helps to reward outcomes when we can, not micromanage behaviors. If what we want is reaching the goal, do not overspecify every tiny motion along the way. Let the policy discover the behavior on its own. Because shared intermediate rewards can help exploration, but every sharing term, every shaping term is an assumption we need to bake in, we need to test. Second, might help to test for loopholes. So before deploying a reward, ask the awkward question, what is the laziest, most creative way to maximize this number without doing what we actually want? If we can think of a hack, the agent surely would think of it and most likely would think of it faster. Third, include costs, things like time, energy, side effects, not making progress forward. There are things that the reward may need to price in, may need to take into consideration. And fourth, keep it simple and inspectable, because every extra term, it creates another place where we have to verify where there's this potential proxy gap. The proxy can diverge from the goal. So a real-world case study makes this concrete. Let's think of YouTube's recommendation reward. Early on, the obvious reward was view count. The system, YouTube, just rewarded clicks. And soon after, creators adapted with clickbait thumbnails and misleading titles. So then YouTube shifted towards watch time. That reduced some clickbait, but it created a new push toward longer videos, autoplay loops, and rabbit holes that kept people watching. Later, YouTube added satisfaction surveys and some other quality signals alongside watch time. That was an improvement, but still not a final answer. And the implication goes beyond AI if we take a step back and think about it. If we think about our own usage of any of these online tools, we realize that the reward function didn't just train the algorithm, it also trained the creators, the users, and the whole ecosystem surrounding it. In fact, more generally, nowadays as AI tools and products enter more aspects of our daily life, the engineering choices that we make would have implications far beyond just those systems alone. And let me end the reward section with a similarly trivial example closer to this room. Suppose we want an RL system to help run office hours. What should the reward function be? Should we minimize wait time, maximize the number of students helped, maximize students' confidence when they leave, or maximize performance on the next problem set? Those are not the same objective, and they would open up different loopholes. A system that maximizes wait time may rush students through explanation. A system that maximizes confidence may make students feel good without actually fixing any misunderstandings. A system that optimizes next week performance may spend longer on fewer students. And that is the core difficulty. Before an RL algorithm can even come in and optimize stuff, someone has to decide first what good even means. And today we have treated that decision mostly as a design problem. Next lecture, we're going to see situations where it's not even our decisions to make. And let's wrap up today's discussion. 5 main takeaways. In RL, the agent collects its own data by acting and observing the consequences. In the standard setup, there's no fixed labeled dataset, just a reward signal that says good or bad. RL is hard even after we know how to solve a fully specified MDP. And the challenges include, well, credit assignment, self-generated data, sample inefficiency, and the exploration versus exploitation trade-off. Any RL problem can be modeled as an MDP with the 5-tuple: states, actions, transitions, rewards, and the discount factor. Modeling an RL problem means deciding what's given and what has to be learned. And those modeling choices matter as much, and sometimes more so, than the algorithm. Agents would optimize exactly what we tell them to, so getting the reward right is again as important as getting the algorithm right, and sometimes even more so. And finally, the proxy reward trap. What's measurable isn't always what's meaningful, and the gap between the two is where reward hacking lives. Real systems out there do not escape this gap by finding or inventing a perfect metric. Instead, they revise rewards, they test loopholes, and decide whose notion of success really counts. And we should keep that in mind whenever we're designing a system that optimizes something, because our design choices, as we've seen, would nowadays have implications far beyond just engineering alone. And next time, we'll see what changes when the reward isn't ours to design. Thanks, everybody. See you next time.